All right, last but not least, I love to welcome Willi and Jonathan. They're going to talk about technical details and implementations for detection, new tools for analysis, and I'm looking forward to the presentation, so the floor is yours.
Awesome, thanks. There you go. Yeah, hello everyone. Thanks for giving us the best slot of the entire conference. What I like about being last is that it's a win-win situation, right? If we go too long, then you guys can sneak out and we won't see you afterwards and it won't be awkward. And if we go too short, you guys get out early and you can drink beer and stuff, and so like, this is good. If we're right on time, then I guess that's maybe a lose situation, I don't know. But anyways, super excited to be here. We are going to dive into a couple technical details around our topic here, and so we'll get into those as well. I guess a quick show of hands. Do we have any malware authors here? Yeah, of course you're not going to raise your hand. Defenders maybe? Red teamers? Okay, we got a good audience here. And we'll try to talk from a number of different perspectives throughout this presentation. But let's get started. Let's not do too much introduction. Well, I guess we better do a little bit. My name is Willi Ballenthin. I'm from the DC area. I work for FireEye. I worked for Mandiant before that, about 5 years. Started out doing incident response, computer forensics, and more recently, over the past couple of years, I've focused on doing specifically malware analysis. Sitting in front of my computer late nights when it's dark, looking at IDA Pro and disassembly views. John?
Hello, everyone. Oh, holy crap. Is this better? All right. So I actually am with Mandiant doing professional services, so doing IR work, forensics, etc. Previously, before that, I was running TZ Works with my dad, building forensics tools, that kind of thing. Before that, I was attempting to be a game developer, whatever. Yeah, so now I'm with Mandiant and exploring all these cool new tools and knowing about, like, here we're actually going to be talking about Shims is a great new way. Well, it's not really that new, but yeah, you want to go to the next?
Yeah, sure. Right, so what we're talking about here today is the application compatibility infrastructure, or Shims. Does anyone here encountered that before? Does everyone here know what it is? Presumably not, that's why you're here. That's okay, we're going to dive into it. But let me talk to you a little bit about how I got involved in them and why I think they're so interesting. So I work on the malware triage queue in FireEye and Mandiant, and we get to see like a fair amount of malware. A lot of stuff comes in each day, we reverse it fairly quickly, try to get a sense for what it's doing, and if it's doing something new, cool, or interesting, then we do a deep dive analysis on it. And so there was this one particular case where we had this like large deployment of FireEye boxes that the client was paying like a lot of money for, and they were getting spearfish emails, and our boxes weren't firing. Now, the client wasn't happy. It doesn't make me feel real good about working for a company whose products don't work, so we wanted to get in and figure out what was going on there. How come our boxes weren't detecting this malware, and the malware was still persisting on the system? So, pull up IDA Pro, start disassembling this thing, understanding what it's doing. And it turns out that this malware was using the application compatibility infrastructure to maintain persistence on a box, okay? So what we had was the main payload that was attached to the email, this phishing email, was a self-extracting RAR, all right? So you double click on this thing, it both drops files on the file system, and it starts executing new code. The content of the code was a couple different files, and the main payload was what we call core plug. Core plug is a malware family. It's honestly typically used by Chinese threat actors, and core plug's used to basically bypass code integrity checking. A lot of times environments will enforce that all executables that are running have to be signed by trusted certificates. Also, what these attackers will do is they'll deploy intentionally vulnerable and legitimate programs that are vulnerable to load order hijacking. And then they supply a load order hijacking exploit in the form of a DLL. In this case, it was elogger.dll. And when they execute this legitimate signed program that is vulnerable, it slurps up this malicious code into the address space and executes it. So it's a tricky way for them to bypass code signing verification. Now, this is a pretty well-known attack vector. We see it all the time. Again, we call it core plug. But what was interesting was actually the payload, the shellcode payload, that ultimately executed and was malicious. And what was going on in there was a whole bunch of different things. It was not SOGU, which is what we typically see in this kind of ecosystem. It was kind of this mishmash of a backdoor with an installer, with a downloader, a bunch of different code families kind of packaged into one. And when it actually went and installed the malware, For persistence, it could do it using a service, but it could also use this application compatibility infrastructure. And that's how it was evading our sandbox. There's 1,000 ways to evade a sandbox, but this is a really interesting one, so we're going to dig into that. So John, want to walk us through kind of the basics of what this thing is and why we should care?
Sure. So basically, what this infrastructure does is it's Windows' way of like fixing applications across their different OSs. So, you know, the transfer from XP to Windows 7 to Windows 8 to Windows 10, you know, it's radically different than it was, you know, 10 years ago. And so they implemented this infrastructure so that it could fix applications that were already compiled, that people are familiar with using, and they didn't want to recompile, you know, whatever they wrote, you know, whatever application they made into, you know, a whole new binary for each OS, Windows OS that gets launched. So they create these fixes, and actually Microsoft uses this all the time. And when you get an update, sometimes you'll see like Microsoft Office, you know, getting updated all the time. Like sometimes, you know, 2 or 3 times a week. Sometimes when they find like different things that are going wrong, different vulnerabilities that might actually cause Office to break, or, you know, Outlook to break, whatever. And so they'll implement these little fixes, and they do this by hooking into the actual Windows API. And these things are actually called Shims, and they're built into these big databases on the file system, and they're basically these binary XML. So what's inside each of these shim entries? You have a file name, a PE checksum, file size, version info, and then you have, so this is all pointing towards the actual target of whatever application you're trying to modify or fix. And what you actually have are these pre-configured quick fixes, and then there's like 407 of them. You can modify an application any way you want it to run. You can inject different shell code. You can, you know, turn off Windows Defender. You can turn on, you know, make it run as admin. You know, all these different little fixes. Or you can virtualize a registry. And we're going to go talk through all of these different implementations. Also, one of the, you know, EMET uses this infrastructure to actually inject its DLL into processes on execution, so that you know, it can analyze exactly what an application is doing. So this is a shim entry for the Oregon Trail, and one of the fixes it's actually doing is, you know, Oregon Trail has been around for, you know, quite a long time. So, you know, it didn't actually have, you know, it doesn't know how to reference this space that's, you know, that large. You know, it can't reference a terabyte drive. So what one of these fixes is, it emulates it for the program. So when it tries to reference something, it can actually say, you know, store files, etc. So this is basically the XML that we pulled out from this entry. So some shim techniques. So here we're actually going to talk about some of the things that we saw, and then you know, how these get created, and you know, what we see in the wild, and then how they're actually deployed. So this is the application compatibility toolkit. It's actually given out by Microsoft for free, and they'll actually help you, if you contact them, they'll actually help you fix your application, and they'll go through like each of these different fixes, and you know, what each one does. That way you can hook into the API and change how your application is actually running. So here I was actually using the correct file paths fix, and you can also actually see on the left side here all these applications that were fixed. So you can actually see like World of Warcraft or Zone Alarm here, and you know, the Oregon Trail, or all these different other applications. Because when you write a shim, Microsoft will actually claim it as property as part of their way to have a reliable OS running the different applications that a user might want to install. So they request that you, well, I guess demand that you send the shim in, so that way when you run an application, there's that reliability that it's actually going to run properly. So yeah, this one is actually using Windows 7, and then in Windows 8.1, it actually has like 407 different fixes that you can select through.
I think we found in our experience looking into this whole infrastructure and everything, that this technology has been around for a really long time. All right, so this is built into the very core of Windows, and actually a lot of people already know about it. From the defensive and maybe offensive perspectives, I think it's kind of new. I didn't know about it until a couple months ago. I don't see much research about it, like I said again, in attacks. But if you look online, this is a very heavily used technology, especially within kind of the gaming industry. And like John was saying earlier, in software development and ensuring that old, obsolete programs still run on new versions of Windows. So it's kind of neat when you're browsing online and you don't find any attackers really using this stuff, but there's plenty of information on gaming forums on how to actually set these things up and use them in your environment.
So as part of deploying it, once you actually create your shim entry, this SDB install will actually install it for you. It'll create the uninstall entry in the control panel, and then it'll create these two registry keys. So that way, when the application actually runs, the OS will say, okay, hold on, I need to load this shim up first, and this is how it knows where to get it. And it'll load that shim, and then whenever a file tries to reference any of the things that it's hooked, it'll redirect it to whatever, whoever made the shim, process it however you wanted it, that shim wanted you to do.
Can I jump in real quick?
Yeah, sure.
Any of you guys, forensic investigators out there, use the application or app compat cache? Found pretty useful, right? You get to see what programs are executing, some of the things that are loaded and when they're running. Well, that's just a performance feature of this whole infrastructure here. That app compat cache is just a feature that allows the system to quickly decide whether or not a new program that's about to execute should be shimmed. So it's interesting now that when that original research first went out, we basically were like, hey, there's this registry key that seems to have really interesting information, and we didn't really know much about it. Why is it there? Turns out it has to do with this whole infrastructure that we're talking about right here.
So, yeah, and basically, Microsoft recommends that you use this to, pushing it out with, group policy, and then, packaging it all in MSI as part of an installer for your application. However, we have seen malware where it actually directly adds these registry values, because this is all you need for your shims to actually run and get reference when an application runs. So it's very easy to circumvent some of these things. And the extra control panel entries. So do you want to go over some of these cool things?
Yeah, let me walk you through. We've been talking this weird infrastructure. Game developers use it. I guess some malware authors use it. And why do they use it? So here are some of just those few out of the 400 or so shims that are available to you to configure using that nice GUI program. So let's see. Disable Windows Defender. That sounds pretty useful. Maybe I create a shim, apply it to my malware file, and then maybe Windows Defender doesn't look at it because that would cause system instability or something. We can correct file paths, and John's actually going to walk us through that in a couple slides, but essentially we can say, hey, whenever you want to go launch a process in this one directory, redirect it to this other location. Okay? We can redirect file system reads and writes. And Mark Baggett had a really interesting presentation, I think 2 years ago at BruCON, where he develops a whole userland rootkit that can hide from AV by basically redirecting all these file system activities. Other things we can do is we can change the directories in which load library looks for DLLs that it's going to load. That would be a pretty neat way of kind of adding new load order hijacking vulnerabilities, perhaps, to a binary. No signature check. There is no documentation on it. I'd like to believe maybe you just no longer verify signatures as you load them. I think we need a little research there, because I think that's going to be a fun one. And then some other good, really interesting shims that we can use. We can terminate process on execution. When they first start up, we can immediately kill them. I mean, imagine you go and you try to run like Process Explorer on your compromised system, you're doing a quick triage on the live box, you try to open it up and it immediately stops. Try to open it again, it just gets killed over and over and over again. Like, it'd be pretty frustrating. Wouldn't be the end of the world, but I'd love to kind of mess with some defender as if I were to develop malware and like confuse them that way. And then same thing with virtual registry. That allows us to redirect reads and writes from specific registry keys to different parts of the hive. So as an attacker, that's a pretty interesting thing to do, right? If you were to say, for instance, target Kaspersky.exe and say, Kaspersky, anytime you try to read from the current version run key under the, I don't know, current user's hive, well, let's redirect that registry read to the local systems hive, okay? And now when Kaspersky tries to go and enumerate those persistence locations, things that'll be executed when the user logs in, he doesn't see anything malicious in that user's hive. He just sees what the system's starting up. And that would be an interesting way to hide malware from only the AV solutions, but not the droppers and not all the other parts of the malware ecosystem. So I think that would be a pretty neat thing you could do. But let's dig into a couple real-world practical instances of what malware is doing and why we should care about this. Because these things are really neat to start with, but there's some even neater things we can do. So I described at the very beginning of this presentation, what kind of motivated us to start researching this topic. It was this instance of core plug and this backdoor that was creating these SDB files, which I had to research and understand. And I learned that an SDB file is a way that malware registers a shim with the operating system and says, hey, next time you see this process run, make sure you shim it and apply these fixes. All right, so I learned about it. And I started to learn how to kind of process these SDB files. When I dug into the SDB file that was being used by the malware, this is what I saw. Well, I've changed a little bit of the name here, so it might be hard for you to identify the client. We have a name for this one particular database. This doesn't affect how the program runs, but from an investigative perspective, this is interesting, because what we found was actually a huge campaign of attacks that reuse the same database IDs. So even though they attack different users and attack different processes, they were all linked by the same database ID. That was an easy way for us to track this campaign. The next thing I saw was this definition of a shim. So this is a type of, this is a specific instance of one of those shim mechanisms. In this case, the DLL file tag says we want to load an additional DLL file at runtime into some process, okay? This DLL file would, in a legitimate circumstances, be allowed to patch up the target executable before it executes. Maybe it can do some runtime patching. In the instance of Emmet, for instance, it can add those additional mitigations to prevent exploitation on the box, all right, enforce DEP and stuff like that. But here, the malware was using this maliciously. It was targeting svchost.exe, and every time that process started, the Windows loader very nicely said, oh, I see that there's a shim that is registered. Oh, okay, when svchost starts, which it starts all the time when the system boots, I'm going to load in this elogger.dll, which is our backdoor. All right? I thought that was pretty cool. Because when I go and investigate the system, I see maybe that there's some malware running, maybe I use volatility or something, and I look at the address space of svchost, and I see this malicious thing in it, so I go to disk and I say, how come svchost is compromised? Like, why is it running out of svchost? I don't see code injection or anything. Well, it's, again, really neat because the definition of these shims are in this opaque binary database format, registered in this really weird registry key off to the side. It's very difficult to identify that these shims are registered with the system. And that's what we wanted to mainly talk about here today, is that there's not really any good methodology at this moment to identify this thing happening. So we'll dig into that a little bit more. So anyways, this was really underhanded. It's very difficult to identify this type of DLL injection.
So this one was what I actually implemented in the lab just to play with it, see how long it would actually take to build some of these things. Takes probably about 30 seconds. I mean, to build one of these shims and deploy one of these databases. So I made this custom, I used the correct file path fix, which redirects the arguments. And then I made this mine.exe, and it basically just launches some other executable. And so whenever mine.exe tries to call this executable, instead, since I hooked the API, it's now going to call the cdump1.exe. So all I did was I simply added this fix, and I said, I gave it this argument. So now I'm redirecting. Whenever I call this, whenever the application calls this, it will now call this. So you can do this for, INI files, bash scripts, it doesn't matter, like essentially anything. It's hooking into the API and redirecting all of these file paths. Why this is implemented is because, in Windows XP, everything was named like, WinNT, blah, 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 or documents and settings, blah, blah, blah. And so this was their way of fixing that and saying like, okay, I want to redirect to C users, or, oh, hey, I want to write to C Windows. No, you're going to go to C users app data or something like that. So this is why they actually put the fix in, but it can be used, for malicious purposes. So this is what this looks like. I made this mine SDB shim database, and then this is my executable, this application that I'm affecting. So it has like the correct file paths and then the argument. So, pretty clear. So some of these, after analysis of this, some of the things that you could actually take away is like, you can modify command.exe. So you could, have some hidden persistence, or, man in the middle, some of these process creation when, say, an app job wants to create something, or, some admin is doing something, you can see exactly what they're trying to do on particular servers, how they're set up. Add some DFIR confusion, so when someone knows that something's wrong because you see something, outbound on the network, and it's like, well, hey, what is going on here on the system? And then you don't actually see anything, because you can actually build all these shims to kind of build a backdoor to exfiltrate any kind of information on that system. And the other thing is like nothing is like limited on these directories. So there's no limitation to what you can modify on the operating system.
All right, and so our third little case study here is about another piece of malware that we've seen in the wild here. This specific malware family, I think it's called GUKit, is kind of a commodity malware family. It's not at this point a targeted threat, but it does some really neat stuff. What makes it so neat is that it installs this SDB file using SDB install that registers in the registry. The system, when it boots up, takes the targeted process and applies a shim to it. Now, what's interesting about the shim is that the shim actually directly patches shellcode into the targeted executable. All right, and only in memory will that shellcode be there, and all the shellcode on disk is obfuscated within this complex database format that basically no one actually knows how to parse right now. That makes detection really difficult. So when I go and I look at the installation for this backdoor, what I see is I've got this unique database ID that I could key off of, except in this case, the malware actually creates a new database ID uniquely for every single installation. So it's not easy for me to go in and just blacklist that particular database ID. Now I don't really know which ones might be related to the attacker. Within that, I see that the malware is targeting opera.exe. And when opera.exe is launched, the Windows loader checks app-compat cache, says, okay, sure enough, I have a shim to apply. What shim am I going to apply? This patch data 0. The definition of that is right here. The takeaway is this patch bits declaration there. This actually contains raw binary data that gets patched into memory at specific locations. This is awesome, all right? Digging a little bit into this, I'll show you in a sec what these patches do. But the capabilities within this patch bits structure, again, it's kind of an undocumented structure there, allows you to first match on bits that you expect to find in memory. That allows you to ensure that you don't corrupt the system by accidentally patching into the middle of an existing function. That allows you to very accurately target specific versions of software, because memory patching is a fragile art. The other thing you can do, like I said, is patch bits directly into memory that are defined in these SDB files. And we can patch both EXEs and DLLs. I'd love to write a little proof of concept that maybe patches a single byte within the, I don't know, SSL verification library that simply always returns true when you go to an internet address. That would be a very obvious application of this type of attack. But this specific backdoor, what it did was it made 3 patches to Opera. And within Opera, it targeted kernel32.exe, which is a standard library used. So on the left here, we have the bits that were matched, that the loader just kind of verified were there in order to not corrupt the memory space. And what we find on the right is the batches, are the bytes that were patched in. So what we see on the left here is that the malware targeted this unused portion of the binary. Perhaps that's some slack space within the sections. They contain just null bytes. And what was put in this place was 2 instructions. We have a call instruction to a hard-coded address and an extra jump instruction. Turns out this jump instruction is never executed. But this is a classic hook, okay? Sorry, I did lie here. These knobs here are not in between sections. Sorry, I got ahead of myself. That's a different patch. These are at the start of a function that's commonly used within kernel32, all right? This is in one of the function prologues. Microsoft actually includes these NOPs, these no operation instructions, in order to allow hot patching during future updates to kernel32. In this case, the malware takes advantage of this existing space at the beginning of a function to put in its own instructions, which again, jump to some malicious code. Seeing what that section looks like, here is that slack space section, a bunch of null bytes, which is replaced in memory with this trampoline here. So anyone familiar with assembly code, x86 assembly code here, will see that this first instruction changes the return pointer, which cleans up the stack after the hook executes. Push AD, push FD saves the context that the program is currently in and allows a payload to execute, and the context then to be restored afterwards so that there's no lasting effects to the program. So that kernel32 continues to execute as expected, but the malicious code also runs. So in between the push AD and the pop AD, we have this call, and this is where the payload of the shellcode backdoor is. And so if we were to look at that, we'd see like many kilobytes of shellcode, which ultimately reach out to the internet, download additional backdoors, and execute them on the system. All right? Pretty cool little setup here. In terms of, I tried to do this animation this afternoon. I love these things when I see other people do them. So this one on the top here is a legit kernel32. When this legit function is called, we would expect all the legit code to run and nothing unusual to happen. Once it's been patched by this particular backdoor, we saw those 3 patches. The first one was a jump at the very beginning of the function. That jumps to the trampoline. The trampoline passes control to our shellcode backdoor, which, like I said, fetches additional backdoors and executes on them on the system, returns to trampoline, and then the legitimate code within kernel32 also gets an opportunity to still run. So it's pretty neat. It's a well-done hook there. In terms of analyzing this is where I really got excited because, I don't know, I feel that when I'm analyzing a lot of these kind of targeted backdoors, a lot of them aren't very difficult to analyze. Like, it's almost like the attackers don't care if they're found because they're already complete in their attack, right? When I was dealing with this backdoor, I was thinking, this is awesome. This is a guy who's gone out and researched how he can use this brand new technology. He's doing it in a way that makes it very difficult for me to analyze. Because if I would actually ask the question, where else can I find this backdoor? Where else can I find these artifacts? I'm not left with very much, right? Because all I have to look at is not kernel32, is not Opera. Those things are not compromised. Again, I have to look at weird corners of the registry and these database files that are kind of opaque blobs of data. even that shell code isn't in one nice section, it's split up all over the place. And so I can't even scan for particular hashes and things like that. It's not a great situation. So, want to walk us through what these SDB files look like? Understand maybe what we can do about it?
So basically, this is what the SDB file looks like. It's just essentially it looks like a blob of data. You can kind of pull some, ASCII out of it, but not really. The app help.dll exposes 254 exports for manipulating these shims. So, you have a lot of different things that you can, or this is how they look like. So what we did was we actually reverse engineered it. Conceptually, it looks like an indexed XML document. So the three main nodes you have are the index, the database structure, and a string table. There's no compression, there's no encryption, there's no checksums or anything. But essentially when you're looking at it, it just looks like a blob of data that it's very difficult to just like read with a hex editor. So you need to build a parser to really understand what's going on.
And although you could rely on like the app help DLL routines, that doesn't really, one, work on Linux or Mac or some of your other analysis systems. Also, I'm always concerned about like, what is Windows doing to interpret the data for me? Like you try to use like a web browser and they go like out of their way to like patch up data for you to make it actually display to you on screen. When I give Microsoft a SDB file, I want to know that it's giving me precisely the information that's in there, no more, no less. And I can't be sure of that if I use apphelp.dll. That's why I think it's important that we know what these database files actually look like, their binary structure, and so we can parse them ourselves.
So Willi ended up actually building this Python SDB, which breaks it down and parses through these shim databases on Windows. So so here's his link for actually when you pull these things down. They actually, it's easy to grab them. I mean, it's not like really a protected file, so you can read them pretty easily. So it's pretty simple to copy them back. So some of our detection methodology, when we're investigating some of these things, I decided to grab a bunch from a couple of IRs that I was doing, just to do some analysis to see if we could actually find any of these things at scale. So, you want to walk through the scenario?
Yeah, sure. So I think the question that we need to consider is, we've demonstrated at this point, like, yeah, if you have a single box and you're doing a deep forensic analysis and you suspect that the shims were used, like, yeah, you can deal with it, right? Like, there's some parsers we've released, there's some parsers some other people have released. You can figure out what's going on. But that doesn't help us at a large scale in terms of detection of this thing is actually happening, right? If you don't have that hint that the attackers are using this technique, are you really going to be looking for it? Let's talk about how you can do that. So as we talk about how we do this, I want to use one more example of malware that I found just the other week. I think it's semantic to text this thing as Mamba shim, and it's kind of an interesting backdoor. It's written in Python, so at first I was like, awesome, py2exe, I'm just going to decompile it and read the source, it's going to be easy. Not actually that easy. It was one of the first times I'd actually seen obfuscated Python bytecode, so that was really fun to kind of like emulate it and figure out how it worked. And then under the hood, it used the ctypes module to directly interface with the native API and dynamically create new SDB files and install those SDB files for persistence. All right. So this is kind of our motivating example here. This is mass malware. It's getting distributed all over the place. How do we know that it's out there on your system, besides relying on semantic to do its job?
So some of the, do we have any ways that we can detect this normally? Like in an admin, as an IT, admin or a security person, if just using like normal Windows controls, there's, the problem is with this infrastructure is that there's no central management for all these SDBs that get deployed. As an application gets shimmed, I mean, it gets, stacked up, or it gets put onto one of the existing databases, and then that might actually be different across the different systems, depending on what gets installed first. So there's also no Active Directory tools for this Shim database management, so you don't know which one's been fixed, which one isn't. You don't know what updates have been pushed to the different servers or different systems, and there's no accounting of these changes or in the actual database, and there's no rollback features in case you did push a shim and then you're like, oh, I want to go back to the old one after I've pushed all these shims up and like it broke everything, So the only win maybe is that SDB install.exe gets called, and then do some process auditing in your event logs or something. But I don't know if that's really a win.
Yeah, it kind of seems like we're on our own because we can't use built-in tools to query for the SDB files. So maybe what we'd hope is like, well, surely these databases are like signed by trusted certificates that are only loaded, appropriately. Well, that's also not the case. Microsoft doesn't verify any signatures when loading these shims and applying them to processes. Basically, if you have administrative rights to the box, then you can install these shims and they always execute until someone takes them away. Okay. So, well, if we can't rely on Microsoft to do the hashing and the verification, well, maybe we can develop a whitelist of all the shim databases that you see in your system and I see on my system. And if we just kind of assume that we're not all compromised, maybe we can just use this whitelist. Well, that also doesn't work because each of these databases ends up being more or less unique to each individual system based on what software is installed, in what order the software was installed, what timestamps are in your database, the database ID, like all these different features. Don't want to dig into the minute details there. Ultimately, what you should take away is that you can't just hash these files and compare them to a whitelist. That doesn't work. So, all right, what else can we think about? John?
So one way was to actually, acquire all of the SDBs on a particular system. It ranged anywhere from like, 50 megs to 120 megs, depending on, how many applications were actually installed on per system. We also did some of where the actual shim databases were actually stored. So like normally legitimate ones are stored in their own program files directory. So to help that application actually run, that would appear normal. Also with Windows, Windows has its own, like in the app patch directory, it will have all of its databases. And some of the ones that we found in the wild, they actually use their, the user's profile environment variable, as some of their working directories. That's where they put the SDB. That kind of stuck out more of like a sore thumb. And then also, if anything's been added, you could inspect the two registry keys showing what has actually been registered on the system. And then we have a list here of like some of the default databases, so all these ones with main are typically the ones that the OS uses.
Yeah, taking a look at my system here, it's a Windows 10 system, not too old. I have those 5 SDB files and then an additional one that was installed by, I think, 7-zip. And those are the only 6 SDB files I have on my entire system. So maybe we could try in a large environment, we could say do some kind of anomaly detection, find out which additional SDBs are installed, maybe look at them that way. But that's not really a great solution still at this point. Like, it's nice when you have the capacity to do hunting. How many of you guys get to do hunting? Ooh. Do you know what I mean by hunting? Like proactively looking for compromises? Doesn't sound like too many people even have the capacity to do that. So it's nice to be able to think about how we do this, but we don't want a solution that relies on that. So if we're taking into account the specific Mamba Shim malware, what it actually did when it was interacting with C-types to create these custom SDB files, it was doing some really, really silly things. They went through a lot of work to do Python obfuscation using these new techniques and everything like that. But when it came to actually using the shim infrastructure, they made a lot of really bad choices. Some of the things they did was there's a timestamp at the beginning of the SDB file about when it was like created. All right, that's a 64-bit value, like a Microsoft file time, and they picked a random number to put in there. All right, So if you think about the time span represented by a file time, that's like hundreds or thousands of years, and they're just picking a random value in there and hoping that it falls within something reasonable. I mean, that's brain dead. You would simply have to look at these SDB files and say, hey, which one were created in the last like 10 years? And most of the time, an extreme majority of the time, you would catch this malware. Same thing with the compiler version. They would just pick random numbers to create these compiler versions. This particular piece of malware is not too difficult to find using some basic heuristics inspecting the SDB files. But what we have to think about is that people a year from now who have maybe watched this presentation or considered in a little more depth how to use this technology, how to really blend it into the environment. What would you do then? You're up.
So there's another artifact that's left behind is actually this, this event log in the app experience program telemetry. And the problem is that when you're actually analyzing these things, you'll see all the legitimate shims that actually get pushed by, so you'll see a lot of Office ones, a lot of Outlook ones.
Oregon Trail, if you still play Oregon Trail, that would be shim.
So all of these things would show up, and using this format, compatibility fix applied to blah blah blah. This application, and then have the fix information. So some of the actual fixes that got pushed. So you would see like the file path one or whatever, and then do you actually have a technology that can go through and parse through all these unusual entries and see which one is the actual outlier and actually alert to something being shimmed, improperly or maliciously.
Yeah, people love to talk about like machine learning and computer security or like malware analysis and stuff. That might be an application where maybe you could just stuff in a huge data set and then it could just tell you like what the unusual entries are. But I think we're like years away from that solution. So until someone develops it, it's a feasible solution, but it's just not there yet. And so one of the final ideas that we have right now in terms of detecting these things is, I don't know, I made up this term, kind of like domain-specific hashing. And what I mean by that is, I already described earlier how we can't simply hash all the SDB files and basically create these signatures and use them to white or blacklist, because each database looks mostly unique. But what we can do is hash entries within those databases, okay? So Microsoft, like John was saying earlier, distributes something like 410 default shims. It has a collection of a few thousand programs it shims by default. Those things don't change from Windows version to Windows version too much, especially from your computer to my computer. All those definitions will still be there, though they may be in a slightly different order. So what we can do is basically come up as a community, or you can simply listen to me in the way that I did it, is hash each one of those different entries. That allows you to create a checksum or a hash, I guess. Obviously, you hash it and you get a hash, yes, obviously. That allows you to build a whitelist that you can look up against your SDB files and decide if the things in the SDB file are legitimate or have never been seen before, should be trusted or not trusted. The benefits of this is that it'll work. The downside is, well, we need to start developing tools that can parse these databases, do it at scale, do it across an entire environment, build up hash sets. There's a bit of work there. But I think what we can demonstrate is that this technique would work should these shimming attacks become much more prevalent.
And then you also have to consider like every Patch Tuesday, adding to that whitelist. So yeah, it'd be kind of a pain. So prepare for this scenario. So basically there's this packer, which actually builds without using the toolkit, they'll actually pull the XML for each of the shims and then pack it into a database for you. And so if you took the sysmain.sdb, which you can't actually access with the toolkit normally, well, I should say at all, but you could parse it out, parse out all the XML, and then repack and inject your own shim into sysmain.sdb, and then you essentially add a new shim for explorer.exe, have your payload, have some keylog data, maybe some shellcode, whatever you want, right? And then repack the sysmain.sdb, deploy it out. Who's gonna find it? So it's just a scary idea, you know, of what you can do with these things, and they're pretty much unchecked.
Right. Yeah, I think right now that, you know, the malware samples that we showed you, we can catch pretty easily. Like, we've seen them, we found them in the wild before. But the big question is, let's say these people actually start working hard, their bosses crack down on them, or offer to give them a big raise if they develop something cool and new. They do something like this, and we're going to be totally left in the dust as defenders. They can be patching in their shellcode into arbitrary executables. We won't easily be finding it. We have no way to scan for it and identify it across the network. And that's a little bit scary. So the idea of this presentation is kind of walk through a bit of this. Can you get the next slide? Yeah. Is to kind of walk through this technology, give you guys an introduction of what this infrastructure is, show you that malware and attackers are actively using this in the environment, in the world for the past year or two. It's becoming more and more common, and to introduce a couple techniques that we could use to maybe find this thing. These are not complete solutions, as you can tell. We still need to develop them more as a community, but this is our introduction to the realm of application compatibility shims. So you're the front line now. Good luck. At this point, we better ask for any questions. I don't know if any of this made sense. If it was interesting to you, let me know what you think. Go ahead.
Maybe I didn't understand.
Yes.
Because it was a long night last night and a long day today.
Of course.
But you described the scenario earlier where you would wind up with different SDB files if you installed Office first, then say Visual Studio.
Exactly.
If I took two machines, and on one I did it in order A, and the other I did it in order B,
Yes.
and then I took the SDB file from case A and I just dropped it on B, is it still going to behave as expected?
My understanding is that it should behave as expected.
So then my follow-on is, if you're talking about a sort of scenario in which you could conceivably do whitelisting, that implies an enterprise or an institution that has a fairly sophisticated mechanism for controlling what's on the endpoint.
Yes.
You're probably doing application whitelisting as well.
Sure.
So if you got like, this is our golden master and we're controlling the application set, you could push out SDB files, say at this patch level, this is what the shit is supposed to look like.
Yes.
Now you hash the whole thing and use tripwire or something tripwire-ish
Yep.
to detect changes. Would that not work? Yeah.
Yeah, I think that's a good solution. I'd love to try it out and make sure it works, and maybe that just solves everything, and maybe this last hour you should have spent drinking. But also, I have a feeling that it's a good solution, and that a mature, company may be able to implement that. But if you're not able to implement that, ensuring that all gold images are precisely up to date on every single one of your computers.
On your father-in-law's PC.
Exactly. Then we need to start worrying about response and detection versus just preparing for the, those compromises and things like that. So I think that's a great solution. I also want to have a backup plan in case we're not able to get to that point.
Thanks. Great talk.
I'm going to work my way to the back, but let me start here.
Hi. Are there shims that affect settings for DEP, ASLR, NX, EMET mitigations, etc.?
I'm fairly sure there are. Yeah, there's some fixes. Yes, so there are.
Bad.
Yes. And also noted, this is how EMET is implemented, right? So basically, EMET, when you enable the programs in that GUI, it basically adds shim entries to inject the EMET DLL into your programs that you want to be protected, and then that DLL is able to patch up the protected program to maybe check the stack and enable DEP or NX and all these things like that. Question in the back? I'm completely locked in.
So this is probably something you've already thought about. So it's interesting questions. But how different are your STD files
SDB to another? Thank you. My voice is killing me. So how different are your SDB files? Could you do something like use fuzzy hashing to analyze differences and kind of get payloads even if the order is different or something like
Yeah,
that?
I think we're basically on the same track there, is that ultimately the chunks of the file are basically the same, yet the ordering may be off and there might be some small fields here and there that are different, padding and stuff like that. And so your fuzzy hashing solution was kind of what I was calling like domain-specific hashing earlier, which is like, I know the structure of this file, I know that this thing is something appropriate to be hashed, so let me hash that and use that as part of my signature for things that should be whitelisted or blacklisted. But we're on the same track there, yes, exactly. The answer is yes. There's how many different ways to specify a program would you say there are? Something like 10? Yeah. You can do like PE header hash. You can do version information. You can do hash of the binary, path of the binary, name of the binary. Like you can do, I think, do certificate used to sign the binary. You can use all these different ways to specify the things that you are shimming. This is interesting both from the defender's perspective, easy way to upgrade all your programs at the same time. Great from an attacker's perspective as well, because you don't just have to shim Opera, you could shim all the web browsers at the same time using a very... I haven't tried it. That would be pretty cool.
As a researcher and as a FireEye employee, can you comment on what happened to 44Con London conference?
I am not too familiar with it besides what I saw in the news along with you guys. It is a big company, and so, yeah, I'm sorry, I don't know. Any other questions? Go ahead.
I'm just wondering, have you tried Shims with, things that run before the user logs in, like sticky keys? Does Shims also get called?
I don't know. I suspect they do, and my reasoning is that the registry path that you use to register the shims is in like the local machine Hive. Therefore, I think it's system-wide. And the implementation of the shimming engine is in the Windows loader. So it seems to me that those things should be shimmable, but that's my educated guess. I don't know for sure.
All right, thank you.
Go ahead.
To the wildcard point, why don't you try shimming the Windows loader?
There's a few things that you can't shim. I don't have them totally enumerated. There's also some protections on there are a few places you can't shim, and that's one of them.
That would just be dirty.
I know. I haven't worked with them. We haven't worked with them directly. So John Erickson out of iSight has done a lot of offensive research, basically taking what he's seen in the field and also developing new techniques as well to show how this can be used. Because this is not a vulnerability in Windows. You need administrative access to the system. It's almost like the desired state configuration talk earlier. It's not a vulnerability, but it can be used maliciously. And so, answer your question directly, no, I don't know. I think an easy thing they could do is maybe do signature verification of the SDB files. That would be maybe a quick win in order to find what should be allowed to load or not, but I don't know for sure.
I believe there was one upstairs.
I'm not sure. We'll have to do some research. Not too sure. Man, a lot of questions. No one wants to drink beer. Let's keep going.
You mentioned the default locations, C Windows and somewhere under program files.
Yep.
In a detection sort of way, would it be a bad idea, do you think, to just look for, say, put an exclusion for if you're looking for stuff under, ignore STBs in Windows and under, say, program files and program files x86 and have a closer look at stuff elsewhere? Just
So
trying to look for a quick win.
you're looking for like shims within program files itself?
that are
or
outside
like,
those those directories?
I was just pointing that out more of like a quick win. So like if you're analyzing and you know that there might be shims involved, that you can actually say like, oh hey, if this is in the users directory, it's normally not a legit like developer, building that shim or pushing that database out. So you would have to start deep diving into exactly what fixes are getting pushed, what applications are getting touched, because like if there's with the event log, you can actually see what application is actually getting modified, and then what fix is being applied to it. So if you're seeing something that is in this program files directory, like, Visual Studio, but hey, it's affecting command.exe, that might be an indicator that you might want to check out what exactly is going on. So.
You as well. So when you're going through and kind of hunting for this kind of stuff, and I'm assuming you've done it at some clients, have you found a lot of commodity malware that has started to use this? So I know we referenced one or two here, but have you seen it just pop up in the hunting phase, or what have you seen?
Not too much yet, because we haven't worked at too many different clients and engagements yet. We're still kind of expanding both our methodology here, making it seamless, making it easy push button to do, and also expanding it to more clients. What we do tend to find, at least the stuff that we've talked about here, is there's both commodity malware that's using this, and it's hard to tell how many threat groups are using this technique. There's obviously one. The question is, how much code are they sharing? Is there 2 or 3? Because some of the malware is slightly different. It's hard to really say. But there are multiple people who are using these shims right now, this technique, and in my limited experience as a computer security person, I expect this to grow in the future. Maybe I should recommend, since I know there's a lot of people here, that anyone who has questions, meet us up front afterwards, and the rest of you guys are welcome to come back next year, because I think it's going to be another really good conference. So thank you.